All right, class. This video is going to work through lesson 3-1 in our textbook, and we're really just going to try to review and maybe begin to expound upon the whole idea of exponential functions. And so let's just start off with example 1. We're dealing with sketch and analyze the graph of exponential functions. And you can see I've given you a couple of charts or a couple of images from our calculator. We start off with the function f of x equals 3 to the x. Now this is different than, say, x cubed. Now that would be your cubic function. And we have all looked at the graph of our parent functions where we have x cubed, and we kind of have an idea of what that's going to graph. It actually, if you can see my cursor, it would go like this. That's going to be the cubic function. But now it changes when I reverse the position of the x and the 3. So here now I have 3 to the x, and I'm going to treat that a little differently. So we know if we plug in 0 for our x, well, that's going to be 3 to the 0 power, which is 1. And it's helpful just to look at the table from your calculator. This is just your standard XY table that you would have produced by hand maybe years ago. But think about it. What if I plug in 1? Let's plug in 1 for x. That's going to be 3 to the first. I'm going to go to 1 to the x, and I'm going to be right there at 3. What if I plug in 2? That's going to give me 9. That would be 3 squared, so 9. So 2 is way over here, and 9 is going to be up in here. But what if I plug in a negative 1? And this is where it becomes a little bit different. I plug in a negative 1 for x, and that's going to give me a 1/3. Because remember, that would become 3 to the negative 1, which I don't like the negative exponents. But remember the rule, x to the negative n is equal to 1 over x to the n. So if 3 is taken to the negative first power, that's actually going to be 1 over 3 to the first power, which would be 1/3. If I plug in a negative 2, that's going to be 1 over 3 squared, which is 1 over 9. And you can see this getting ever so closer. You can see the line right here, the function getting ever so closer to the x-axis, but it's never going to quite reach it. So this is your standard exponential function, the way this is going to graph, going from the right to the left. Well, let's look at this example. All that we have changed, well, the 2, but then look at the exponent. We've changed it from a positive to a negative. And what this negative does is it causes it to open the other way. It essentially mirrors it across the y-axis. So in this case, if I plugged in 1 for x, that's actually going to be 2 to the negative first, which would be 1/2. So if I were to plug in 1, I'm going to go to the 1/2 power. But what happens if I plug in a negative 1? That would be 2 to the negative of the negative first. Negative times the negative is a positive. That would be 2 to the first. So I go into negative 1, and I go up to 2. All right, going to be right in there. All right, so when we see the negative here, this is the application. This is what they're really trying to teach us here, that when we change the sign from a positive to a negative, it is going to, instead of opening this way, it is going to reflect it across the y-axis. Let's look at a few examples. Here I've got 3 different graphs up on the chart. We'll go ahead and look at the yellow one first, y6. That is going to be 1c. So I've got 0.25 raised to the x power plus 1. And you can see what it's doing there. All right. All right, so when we're looking at 1c, 1/4 raised to the x plus 1, you'll notice that it's opening from left to right. And as we think about it, well, wasn't that when we have a negative exponent? Because when we have a positive exponent, it opens from right to left, if you think about it that way. And the negative exponent made it go from left to right. So wouldn't we expect, since this is a positive x, wouldn't we expect it to open something more like the green function? And the answer is no, because when we think about this 1/4, we can also write that as 4 to the negative x. You might be able to see it this way. It would write just like this. We could also say, well, that's 4 to the negative x, and we're just using that negative exponent property there. Look what happens when I graph it. Look at that. It's the exact same line. And so that is what's happening there. That is why this one opens from left to right. Well, what about 5 to the x? Which one is that? All right, that is going to be the green. I'm opening 5 to x. Let's play around with it and see. What if I plug in 1 for x? All right, that's going to be, if I plug in 1 for the x, that's going to give me g of x is 5. 1, 2, 3, 4, 5. It's going to be right there. What happens if I plug in -1? Well, that would be 5 to the -1 or 1 over 5 to the +1. So -1, and that's going to be approximately 1/5, just there above the x-axis. And this one is something we expect. 6 to the -x, it's going to flip or mirror across the y-axis, and that is the magenta line right there. Let's play around with that. What if we plugged in -1? So -1 on the x would be right here. That's actually going to give me 6 for f of x. So 1, 2, 3, 4, 5, 6 right there. And you can see how those plot. All right, let's move on to example 2, graph transformations of exponential functions. Now, one thing that doesn't show up is, what is the magenta line here? And that is going to be f of x equals 2 to the x power, 2 to the x power. And we're going to call that our parent function. That's what we're starting with. And so we're looking to see, what does the +1, what does the negative, what does this -3 out here, what does it do to that parent function? So let's start with 2 raised to the x plus 1, and you can see what it does. It raises it up. That's going to go up 1. Think about it. If I plug in a 0 for x, that's going to give me, plug in a 0 for x right here, that's 2 to the first. 0 for x, it's going to go up 2. But if I just have 2 to the x and I plug in 0, I get 2 to the 0 is 1 power. So it's lifting everything up. You can see it kind of tightening it up towards the y-axis. That's what the +1 here is going to do. If that's a 2 or a 3 or a 4, it's going to tighten it up even more and draw it closer to the y-axis. Well, what about the next one? 2 to the -2 to the -x. That is simply the exact same function reflected across the y-axis. And then what happens when I do -3 times 2 to the 2x? Times 2 to the x power. Well, here is our parent function here. And so it looks very similar. Why does it open down? That's the first thing we'll look at. It opens down because of this negative right there. And then you can see it begin to tighten it up just a little bit. That's a result of the 3. So if you were to graph -3 times 2 to the x in your calculator, hit the table function, and you can see what I'm talking about with these x, y's. It's going to tighten it up a little bit closer to the negative y-axis. All right, so here's 2a, 2b, and 2c. I would encourage you to look in your book and give those a shot. You can pause the video and then come back and let's work through these. All right, so in these examples, the magenta is f of x equals 4 to the x power. And so you can see how those are going to be the same in each one. So what happens when I do the -2? Well, in class, I've called this a k value, and that relates back to a previous lesson. And you can see how it simply dropped it straight down 2 units. The negative out here, this is 2b, it reflects it across the x-axis, so it begins to point down. And the +2 ends up sliding it over. All right, it ends up sliding that thing over a little bit. And you can punch the number on the tables to see how that's working. What about 2c? In this case, I have the -x here that is mirroring it across, all right, its point. But this 2 kind of begins to tighten it up and slide it and tighten it up towards that y-axis a little bit. So this number out here is what's changing that little bit of that vertical shape that you're noticing right there. Let's look at example 3, graph natural base exponential functions. And so we start off here, we're kind of elaborating on the whole idea of these exponential functions, and we're including something called the natural base. And it's an irrational number. And so in front of your calculator, you'll see a little blue E. It should be just above, it should be on the natural log key. If you hit second natural log, you'll get your natural base. And you can look in your book and see a better explanation of where they're developing this natural base from. E. It's developed out of the limits. For the purposes of this video, we're not going to take the time to go through that. For now, we're just going to work on it as a constant. It's a rational number that we're going to use to help solve some problems that we'll come to in future chapters, future lessons, I should say. So what happens with e to the x? Now the magenta line is e to the x. We're going to use this as our parent function. So what happens when I put a 4 in front of that x? Well, as you would expect based off past lessons, it tightens it up, because if I plug in a 1, instead of just taking e to the first, I'm now taking e to the fourth. And so that f of x value, or in this case a of x, is going to be a larger and larger number. What happens if I make it a negative x and then plus 3? Well, the negative flips it over the axis, so it reflects it in a vertical, across a vertical plane, but then the plus 3 here lifts it up 3 places. Well, what happens when I do 1/2 of e to the x? All right, that's going to drop it down. Now think about it. If I plug in 0 for x, that's going to give me e to the 0 power, which is just going to be 1 times 1/2, and so I'm right there at 1/2. All right, so basically what that happens is, if we plug in 0 to our parent function, we're going to have, let's see, the parent function. So again, the parent function is simply e to the x. So if I were to plug in 0, it's going to be e to the 0, which is 1, which is right there. 1/2 e to the x, if I plug in 0 for x, again, I get the 1/2 times 1. What if I plugged in 1 for my parent function? That's going to be e to the first. Now the natural base is 2.7182, and again, it's an irrational number. It just keeps going. And so that's going to be approximately right in there. But what happens if I take half of that number? It's going to drop down. So the 1/2 flattens the apparent function, and that's what you have in the green line. All right, so let's look at a few examples. I'd encourage you to pause this, take a look at it, and then after you've tried these, let's come back and look at them. Again, our parent function is going to be e to the x, and that's going to be the magenta line, the natural base, written as an exponential function. We're just raising it to the x variable. What happens if I plug in a negative? Well, by now I hope you know that it just mirrors it across the y-axis. Ex to the minus 5. All right, it's going to stay the same. It's going to open, let's say, from right to left, but that negative 5 here is going to drop it 5 units. What happens if I take the 3 on the outside? Well, by now, the pattern, I hope you're seeing it, this larger than 1, when this number is greater than 1, this a value greater than 1, think back to some previous lessons in chapter 2, I am going to elevate, in this case, t of x. So if I were to plug in 1 to e of x, all right, there's my natural base right there, about 2.71. But what happens if I put a 3 out there? If I plug a 1 into this equation, I'm going to multiply the natural base by 3. And I'm going to be much further up. And so this number, this a value here, we'll call it, when it's greater than 1, elevates the output and draws it closer to the y-axis. All right, I'm going to pause this video here, and we will do examples 4 and following in a subsequent video.